We're now on part B of the problem, okay? What if our power factor is now 0.95 instead of 0.5? We're going to go through this process we just did again. So the first thing I'm going to do is find the apparent power, which is P over the power factor. The apparent power is 1.053 megavolt amperes. And you should be checking me to make sure I'm getting good numbers. That's the average power over the power factor. So theta equals theta V minus theta I, and this is the arc cosine of 0.95. What's that angle? The arc cosine of 0.95, 18 degrees, okay? So my complex power is now 1.053 with an angle of 18 degrees megavolt amperes. So the first difference we see is we went from 60 degrees to 18 degrees. We went from 60 degrees to 18 degrees. So now we're going to find our current. Our current is S over V conjugate. So that is going to be 1.053 with an angle of 18 degrees over 10 kilovolts with an angle of 0 degrees, and then find the conjugate. What is my new current? Well, you can see it's going to be, since it's divided by 10, 105.3 with an angle of negative 18 degrees. Right? So our current was 200 and it dropped by half. It's now 100. So now our new voltage is Vs equals the voltage at the feeder plus the voltage at the load. So that's going to be 2 plus J8 times I plus 10 with an angle of 0 degrees kilovolts. The voltage at the source is going to be 2 plus J8 times I plus 10 kilovolts with an angle of 0 degrees. 10.49 with an angle of 4 degrees in kilovolts. So another good thing is we went from needing 11.59 volts to 10.5 volts or kilovolts. So the voltage at the source is now also less. I only need 10.49 kilovolts to supply a load with 10 kilovolts. So now, what about my voltage regulation? My voltage regulation is the voltage unloaded minus the voltage loaded divided by the voltage loaded. So that's now going to be 10.49 minus 10 over 10 times 100. 10.49 minus 10 over 10 times 100, which is 4.9%, which is less than the 5% that we said we wanted to have our voltage regulation. So by improving the power factor, I can get the voltage regulation less than 5%. We also wanted to improve our efficiency. Our efficiency was P load over P source. So we need to find P source, which is the real part of Vs times I conjugate. So this is going to be the real part of 10.49 kilovolts with an angle of 4 degrees times I conjugate 105.3 with an angle of 18 degrees. What is the power at the source? Very good, Sage. 1.02 megawatts. Okay. So that means our efficiency, and notice that's also less than what it was before, is 1 over 1.02 times 100. Our efficiency is now 1 over 1.02 times 100. What is it? 98%. Okay, so that improved because originally it was 93%. So that's also better. Questions? Okay, we're not done. Get out some paper. This problem is still going. Why did I put this problem on this lecture? It's the problem that's never going to end. Okay. So now if we look at this in terms of cost, let's say electricity costs $0.05 per kilowatt hour, okay? How much money did we save by improving the power factor? Because that means we have to deliver less electricity. So how much money did we save by improving the power factor? So by improving the power factor from 0.5 to 0.95, the power was improved by 57.8 kilowatts. Right? Because originally the power at the source was 11.59 kilowatts. Then with the new power factor, the power at the source was, wait a minute, I wrote down the wrong number. 1.08, sorry. Originally the power at the source was 1.08 megawatts. And now the power at the source is 1.022 megawatts. So if you take the difference between those two, what do you get? I hope it's 57.8 kilowatts. Or something in the ballpark of that. Maybe it's 58 because I rounded. Okay. Well, let's just to be consistent, let me make it a 58. Okay. Okay, so here's the power factor at 0.5. Here's the power factor at 95. And if you subtract those two, you get 58 kilowatts, right? So now I have saved 58 kilowatts. So how much money did I save in a year? I take 58 kilowatts times 24 hours times 365 days, that's a year, times 5 cents. So how much money do I save in a year? Yes, Brendan. Let's say $25,000. 25,000, right? Approximately $25,000 per year, okay? So that means it would be worth your time to invest in finding a way to improve the power factor. This is what we call power factor correction, and you add a capacitor bank into your circuit to improve the power factor. So that's what we're going to do next. So the way that you improve the power factor is in your original circuit, you add capacitors in parallel with the load. The way to improve the power factor is you add capacitors in parallel with the load, and we label that JXC, right? That's the reactance of a capacitor, JXC. Or in terms of the power that you're adding, it would be JQC, right? JXC is the impedance of the capacitor, or JQC is like the reactive power. So in order to improve the power factor, you add capacitors in parallel with the load. So you now have a load that we'll call PL plus JQL, which is our new load, that needs to have a power factor of 0.5 lagging. So to do this, we let PR equal PL. So that means we don't mess with the reactive power part because we're happy with that. We just change Q. So if you think about it like this, we have two power triangles. And the power part is still going to be one megawatts, because that's exactly what we had for the load originally. So that part doesn't change. But we need to change the Q. So assume that originally we had that power factor of 0.95, and we now want the power factor of 0.5. So we found that that angle was 60 degrees, and that angle was 18 degrees. Right? That's the arc cosine of 0.95 and the arc cosine of 0.5. So over here, our Q was J1732 kVar. And over here, it's J329 kVar. Can anybody tell me how I'm getting these numbers? How did I get those two vertical values on the triangle? Nobody remembers my cute saying yesterday? Trevor? Chief Sokotoa, right? Right? So this is the tangent of 60 degrees equals opposite over adjacent. I have the angle, I have the adjacent, I need the opposite. So I'm getting these two values just by solving that triangle. Yes?
Where does the imaginary part come from that?
Well, these are real and imaginary parts. This is what our plot looks like, right? Remember, this is always the real axis and the imaginary axis, whether I'm talking about power or impedance. This is Q. Think about it like this. This is Q and this is P. P plus JQ gives you the magnitude of S. So the difference between those two vertical numbers is what our capacitor bank has to give us. The difference between what we need and what we have is what we need the capacitor bank to do. So if we call this the current load, and this is what we need, the required, the difference between those two values is the capacitor bank. What I'm going to have here is 1,000 plus J 329 kVar and 1,000 plus J 1732 kVar. You subtract them, and you get around negative J 1400 kVar. That's what we need the capacitor to be. The capacitor adds this value. Okay, we're almost done. I have 3 minutes. I'm trying to finish this problem. So that means that XC, or the value of the capacitor, should be 1 over omega C, where QC is the magnitude of the voltage squared over XC. So this is going to be XC equals 10K squared divided by 1400K. So you solve for XC and then use XC to get the capacitor value. So I'm getting around 71 ohms for XC. And then you stick 71 ohms in here to find the capacitor. So the capacitor equals 1 over XC times omega, or 1 over XC times 2 pi 60, which is 37 microfarads. And believe it or not, that's the end of the problem. Good Lord Almighty. Okay. So you saw what it looked like with the old power factor, with the new power factor, and how you add capacitors to improve the power factor. We will do the rest of this lecture packet on Monday. I pray the rest of the problems are not this long. Read over the weekend. Start on your homework over the weekend. And have a wonderful weekend.